Yeah.
I don't even, so I don't hate your meeting.
Oh, no worries. I understand. It's pretty common for night classes to have crazy schedules, so no worries about that. You could call me, Michael or something if you like, or Jacobson. I respond to a lot of stuff, it turns out. Well, looks like it's time to start. Welcome back, everyone. So I have a couple of notes here, but when we get started, I usually have to clear these out so we can start moving around the Moodle website. But each time if you see notes on here, the guarantee is I'm just putting down doodles. These come directly from the notes, so you're not really losing anything if you didn't copy it down in time. But let's get started with a few announcements. My first announcement is that thing. We were asked to put a link called course materials on all of our Moodle courses. It only works on one. I don't think it works on this one. I put it up this morning. Have anyone tried this link in this class? It's supposed to be relative to the book bundle. It sounds like they don't have things working the way it should be attended.
Yeah, I looked at it and it said like 5 courses and 0 materials.
Yeah, it's same for me. This is what it looks like on my end. It says
Yeah,
it's about 24 courses. Things just seem kind of broken on that. I'm gonna leave the link here just in case it gets fixed, and the administration did ask us to put it there in all of our classes, but hopefully they can figure out what's going on with that kind of stuff. So for the moment, I'd say give it a try. If it works, great. If there's nothing there, then I wouldn't worry too much about it. We also mentioned before that if you're working at out of older editions of the textbook, you're gonna be just fine for this class. The way the homework assignments are working are highly traditional. And if you click on assignment 1 or on the assignment 2 down below here, it reveals a PDF at the very bottom. And when you click on the PDF, these are the actual exercises that are coming out of their most recent edition. So if you're in the 5th edition, 6th edition, 7th edition, so on, these are the ones that you'd be studying out of. And it does make it a fairness issue because it almost seems like if you now have the latest edition, you have the answers to the odd problems. So I put down below the answers to the odd problems. So even if you have an older edition, you can look at these and see how they go. I didn't necessarily write out all of my answers exactly like the back of the book in the 9th edition. This is how I ended my answers. So you might see some algebraic differences, some common algebraic forms. The back of the book might have distributed cosine into that group. So I just stopped my answers where it felt natural. So that's where I left these off on. We'll get in the habit of doing that for every one of the homework assignments. And if I ever miss a file, just let me know. I'll be sure to produce it. So it should be there for 7.2 as well. So pretty much that's how the cup is going to go. I think I did add some other materials onto the website. Let's see here. I added this ISU tutoring link. If you click on this, it opens up to, let me see if I can click on it correctly. Left click on it. It takes you to the ISU tutoring page where you can find information about math support. It shows hours, but these hours are relative to the Student Success Center in the Rendezvous building, Pocatello main campus. I tried clicking on this link and let me show you the experience for Idaho Falls tutoring. Oh, I didn't expect that. Let me see what this takes me to. It didn't work last time. It might be updated. No, if you click on that link, you get to some software gore right here, but they'll get that going at some point soon, I'm hoping. So looks like the Idaho Falls tutoring link is not working at the moment. But usually on this campus, tutoring starts on week 2. Week 1, they're still figuring things out, it looks like. There's other things you can take a look into. You might use the online math center. And you can also, let's see here, schedule appointments, things like that. Clicking on math support takes you to a huge Excel style web sheet. And here it says you can scroll through course tutors below to see if someone is currently tutoring for this course. So I went down through here, down, well, doesn't quite scroll the way I want it to. That is weird. Just use the bar. And all the way down here in math, it's kind of a shame. There's not a lot of calculus 2, but there are some calculus 2 tutors that are available here. I'm not sure if any of these are on the Idaho Falls campus. So that's one of the things, again, it's a little bit tricky about tutoring here. But there's other different ways to get support. So take a look at this page, poke around on it. If you have any questions, I'll try to figure out what information I can. But those are so far the new things I added to the Moodle website. Aside from that, I made a revision on these notes here. It says revised August 20, I guess that was yesterday. And my change was, let's see, the derivatives for inverse tangent, inverse cotangent, I took off this list. This is a list of formulas that you're expected to know on exams. They wouldn't be provided. You could put them on your own sheet of notes when you come to take an exam, but these are the ones that are assumed known. So we have to know our trigonometric derivatives, mix, exponentials, and hyperbolics. The ones I took off are over here now. Let me find out where they left. So this is a table that I'm going to include on the last page of the exam. I'm probably going to update this a couple times. I think I want to include a quick trig since we'll be getting into a lot of trigonometry. And on this table, these are the derivatives that I feel like they're good to memorize, but this is a tough list of derivatives to memorize. I think a lot of people are familiar with tangent, cotangent. In this class, they come up a lot. You'll probably have those memorized. But if I were to ask you for the derivative of secant inverse, that's a tough one. I personally review these with a worksheet type thing before I come to class, just so I remember all of them in case they come up. So those are, I feel like, are not things, you don't have to memorize every single spec of Calculus 1 on exam. And I'll try to give you a clear indication of what is going to be included on the last sheet of the exam, what things you have to have memorized or ought to consider putting onto your formula sheet. I think that's my main announcements for so far, folks. Any questions, comments at the moment? Okay, well, we left off here. Let me see if I can bring that back. We left off in section 7.1, not very far. Example 1, example 2 is kind of get everyone on the same page type of material. Some of the problems there are really pretty tricky, but the main result is this integration by parts, which we'll be getting into shortly. So let's jump in. And here's where we left off. Instructions on these said to just simply integrate. It did say check your answer by differentiation, but that doesn't actually apply to every single problem on here. It won't apply to part B. But again, a lot of these are actually kind of tricky in my opinion, especially if it's been a long summer. If you didn't take Calculus 1 during the summer, it could be a little bit trickier as well. But let's take a look. This one says integrate, or better said, find the antiderivative. There's no lower or upper limit, so it's an indefinite integral of the derivative of x sine x. Anyone see how something like that should come out? Yeah, go ahead.
When I first looked at it, I thought it was just kind of an identity problem. It was the integral of a derivative,
Exactly, yeah.
but then I did it, and I did the product rule, I think. You came up with the same answer too.
Yeah, you could actually directly calculate this. Yeah, so if you want to, you could differentiate and then integrate. But like you said, it's the same answer. It's asking you to take an antiderivative of a derivative, and those operations will wipe each other out. So the whole thing becomes x sine x, but it is an antiderivative. We're expecting an entire infinite family of functions, so we just have to put on a constant. And that's the whole story of that one. Again, kind of a weird problem. Some of these are longer, some of these are shorter. On the one above here, we used a full, let's see, U substitution in order to solve this one. So this is one of the faster kind of problems.
Then you did it.
Oh, no worries.
Okay. So I did it using the product rule,
Mhm.
which was like a longer roundabout way to get the same answer.
Yeah, that'd absolutely take you there.
And I was a bit confused as to why that worked, considering it was identity. So, 'cause I mean, we do it as a product rule. Aren't you essentially doing it as if it wasn't integral derivative?
Not necessarily. If you did the product rule, your whole integrand would just turn into something along the lines of sine x plus x cosine x, and then you just have to integrate that. But then your x cosine x integral, that's a whole integration by parts just on it in and of itself. So another way, you said it's kind of like an identity, and here's the way to think about this one. Essentially, you're just taking the antiderivative of a derivative, and each and every time, you're just gonna get the function f of x without the derivative sign on it, plus a constant. So we took here, the function is x sine x differentiated, but the result will always come out like this. So that's the idea behind that problem there. But like you said, there's more than one way to tackle this kind of problem. But it's kind of cool to know sometimes these things are just done directly. And in Leibniz notation, it would look like this. Integrate d by dx, f of x dx, just becomes f of x plus a constant. I think this is kind of a fun way to visualize it too, because it shows how f of x is just popping right out in that whole kind of process. Well, this is something we'll see that comes up here and there. So again, they seem like weird trick problems, but they're actually relevant. We'll see this kind of stuff coming up here and there. Other questions with our part B? Okay, now part C is just like part A. You can solve this by a U substitution. But the trouble you get into with a class like this is there are some integrals you probably don't want to solve by U substitution. It just takes really, really long time. Let me show you an alternate way to think about this one. First, think about what is the antiderivative of a sine. Derivative of a cosine becomes negative sine, so we have to go negative, put a little space there, cosine 3x. I have to add a constant and everything to the right, but this is how I would attack a problem like this. If it's almost just a sine x, but you just have a constant times your function, a 5x, maybe a 3x plus 1, consider going this route. All you now need to do is fill in something here. Anyone see what the number should be by the question mark? Exactly. We take this 3 that we saw here, and we see again there, go 1/3, and plus a constant. At that stage, your derivative is, or excuse me, your antiderivative is completely done. So at the end of the day, if we see something like this, I would probably do a U substitution for something more built up. But if it's simply a function with a constant multiplying or a linear function where x was, this is a really great approach. My instructions said check your work by differentiation. Let's check this one out just for the fun of it. So here's the check. We would take our whole answer, negative 1/3 cosine 3x plus a constant and differentiate it. If you left out the constant, it's okay because it's a constant. It'll go to 0 upon differentiation anyways. So sometimes people focus just on that for the check. But now we're reviewing derivatives. This constant negative 1/3 is multiplying cosine. That means the differentiation operator does not affect it. Negative 1/3 goes right where it is. We move over to the factor cosine. The derivative of cosine is a negative sign. And now I have a lot of negatives. I'll go like this. Negative sine. And then I'm doing this structure. The purpose of all of that is when we did the check, when we're doing the check, this is a real chain rule process. We have a cosine function as the outer function, 3x is the inner function. So when you go to differentiate, you differentiate cosine first. There it is, negative sine. You throw in the input, 3x. And then you differentiate that input, 3x. So that's our review of our chain rule. Some people might do this really fast, and you might have just put 3 because you're anticipating this derivative. So if you do it that way, I'd say that's a perfectly natural way to do it as well. So derivative of this 3x is just a 3. That 3 cancels with this 1/3, and it's going to leave behind negative of a negative sine 3x. We obtain sine 3x, which is the original integrand way up here, and that tells us the check is valid and complete. So it's kind of interesting. The check, in my opinion, is a little bit harder than the actual problem right here, but that's how derivatives integrals go. Sometimes one is far harder than the other. Usually it's integration that's harder. But any questions at all, folks, on part C there? Okay, so that's Another one down. And part D is a massive trick question. Notice the difference though. Part C is an indefinite integral. Your answer is a function. And you can differentiate that, get back to your integrand. But this is a definite integral. The answer here for whatever the integral of x sine x is, and we can calculate it if we wanted to, we just need integration by parts. So we're going to do it a different way. But whatever the answer is to that, it's just a finite number. Anyone see what the whole thing should come out as then? This is one of those really kind of subtle rules. Yeah, go ahead. Absolutely. This is really just the derivative of a constant. The derivative of a constant in any form is always zero. It's just not always easy to see that it's a constant. Let's put down some quick examples. If your function was this, y equals, how about natural log of 7.1? That's a weird constant, but it's more clear that that's a real constant. So you would say dy dx, its derivative, must be zero. But likewise, that's just a number, it's a constant. So whatever that number is, differentiate the constant is what's being asked, you would get zero each and every time. So provided that integral exists, it does because x sine x is continuous from 0 to pi. Well, it's continuous on any domain. So that's just going to be the answer to something like that one. The purpose of part D is just a reminder of the constant rule with differentiation, but also a reminder that constants don't always look like constants like this one here. Any questions at all, folks, with that last review question there? Okay, well, congratulations. We've gotten through the review part. That's not an entire review of Calculus 1, but we are essentially reviewing Calculus 1 every single day that we're in this class. And if questions come up from concepts that just seem like they're a little bit rusty or back in the day, don't hesitate to ask about them. I'll be happy to clarify and put in some of those reminders. So let's now go on to the new material, integration by parts. So when you read this, it's, in my opinion, kind of a tough read. It says, suppose u equals f of x, v equals g of x are two differentiable functions on the domain AB. The derivatives have to be continuous on AB so that we can integrate them. Then this happens. And the question you might have is, what does that have to do with anything? Where does this all come from? So I felt like I put some space here. I should have put a little bit of space here. Let's do a derivation. We don't do derivations a lot in this class. Our author does a great job of deriving a lot of these formulas. But one reason we might do a derivation in class is it's just going to remind us of a bunch of things that we're about to use. So here's a bunch of information that's both a review and a preview that's going to help us out in this derivation. I want to derive this formula right here, but to get started with that, in integration by parts, we often begin with this table. It'll be u equals f of x, and it's going to be a dv equals g prime of x dx, v equals g of x, and du equals f prime of x dx. So when you build out this table, you usually start with the first row. You're setting the values of both of these things. But the thing to focus on, what we've done here is, I have a function u equals f of x, and down below, that's just the differential of that function. There's another function v equals g of x, and up above, that's its differential. So whenever you're using integration by parts, two differentials enter into the picture. It's kind of cool in a way. And this is the major punchline with integration by parts. We're trying to undo a rule of differentiation, much like, say, up here, we undid the chain rule when we did the u substitution method. So what integration by parts attempts to do is take this thing, f of x, g of x, prime. We're in a certain sense undoing the product rule, just not in a direct sense. It's a roundabout way of getting there. But this is part of review as well. If we were to do a product rule here, lots of ways to write this out. Any volunteers for what should be on the right-hand side? How about someone over in the Zoom class? Anyone on Zoom see what should go on here towards the right?
Would the first half be f of x times g of x minus the integral of so you're setting your v to f of x, correct? No, sorry, you're f of x. So I'm still working through this.
You're okay. I think what you're thinking of is possibly this formula right here, just the actual integration by parts formula right here. But down here, we're just going for the ordinary product rule itself. You're on the right track though. Yes, up here.
Just part of what I said, f prime of x times g of x, plus f of x, g prime of x.
Exactly. So thanks, folks. We're on the right track with this. All we did right here was product rule. Now that we've got the product rule, let's hold that thought for just a moment. And remember this trick question. The next thing that happens on integration by parts is we slap all sides of this with the integral sign. We could do it on this step, but it gets a little busy. So I'm going to write down another line. I didn't remember to put in the space. We want to integrate the left. So it's the antiderivative of f of x, g of x prime dx. Integrate the right-hand side. And I'm also going to use the sum rule for integrals and break it up into two different integrals. We'll integrate this first part. Plus, then a new integral for the second part. And we're essentially on our way. And let's take a look at what we've got so far. Here's where color coding starts to become a great idea. On the right-hand side, we've got a f prime of x dx. That's a du. We can throw that in on the next step. We have a g of x here, and that's just going to be v for g of x. On this integral, we have g prime of x dx. I think I'm running out of colors. Let me not highlight this one so it doesn't get, if I'm highlighting everything, it becomes limited value, I think. But that part becomes just a dv. Yeah, go ahead.
Just by different force materials, and it's 4 force and 0 material.
4, 0, yeah. So still not working. If you came in a little bit later, that's irrelevant to this new link right here. The administration asked us to put it on all of our courses, whether it works or not. So looks like so far it's not working, but I'll check it myself a couple of times here and there until we get better information about whatever that was supposed to do. Thanks for mentioning that. Okay, so we've got things color coded. We're going to make some substitutions on the right. But on the left-hand side, it's another take the antiderivative of derivative, just as we did right here. So the left-hand side is just f of x g of x equals. Now we have an integral here. For f prime of x dx, that's altogether a du. So we have, let's see here, g of x, that's the value v. F prime of x dx, it's in a different order, but multiplication's commutative. You can change these around and you get your du. Put that in black again. By similar token, let's see what happens to this one. It starts with an f of x, that's u. G prime of x dx turns into a dv. And on the left-hand side, well, we can just relabel that uv. So here's what the formula looks like so far. F is u, g right here is v. This is set equal to antiderivative v du plus antiderivative u dv. And this is integration by parts. Let's hide this right here now that we're done with it. But in integration by parts, there is 3 different terms. There's really effectively 3 different formulas altogether. It's just what's decided. This is the easiest format to go with. So when people write down the formula for integration by parts, they solved for that integral. Subtract v du from both sides, and that's this portion right here of the derivation. So we're basically there, we have the right equation, we just have to solve for u dv. This is like an ordinary equation, all of these are functions or quantities, so just subtract integral of v du. I'm gonna write this side first, integral of u dv equals uv, like it was mentioned earlier, nice and integral of v du. So that finally gets us up to this right here. That's our derivation of integration by parts. And each and every time you do this, this table is also fundamental. You're given some kind of integral, like say, this one down here. You have to decide what are the parts, what is the u, and what is the dv. It all comes together into this nice and slick formula, but selecting what u has to be, selecting what dv has to be, that's sometimes the hardest part about all of this. The good news is there is a pretty decent mnemonic that works most of the time that we'll give it a look at. But first, any questions, folks, where this came from, looking at that derivation? It's really weird. I like to think of integration by parts as you undid the product rule, but that's not the whole story, right? We undid the product rule, we integrated, then we rearranged that resulting equation to land there. So in a roundabout way, we're reversing a product rule. Let's put it into action next. So like we were mentioning, one difficulty is deciding what u should represent. Once you decide u, the rest is not as bad getting dv, but question first up here.
When you get to the object, I guess.
Gotcha. This is the mnemonic that works pretty much for any problem that I would assign in this class, certainly on exam problems. It's not something that's going to 100% work every time, but it's a great starting point. So what the laite, or however it's really meant to be pronounced, is referring to is this. Pick u by first selecting L logarithmic functions. So if you see a logarithmic function anywhere in your integral, what this acronym or mnemonic is trying to say is that's the right choice for your u when you go to build out this table right here in integration by parts. If there is no logarithm, we move over to I. I stands for inverse function. Think cosine inverse, tangent inverse is usually what's being meant there. So I is an inverse function. I think that one deserves an example, so let's put it in. So for example, something like secant inverse. If you see a secant inverse, tangent inverse, anything along those lines in your integrand, that might be the best choice for your inverse function. But it's kind of not a perfect mnemonic when you think about it, because, for example, y equals e to the x, y equals natural log x, that's a pair of inverse functions. One of them is a logarithm, one of them is an exponential, e is for exponential. So again, it's not a perfect mnemonic, but it does a great job. So let's move on to the next. Anyone happen to know what a would represent? Going in the similar spirit here. What kind of function would a be? Exactly. Algebraic would be anything along the lines of x squared plus 7x, maybe square root of x, those kinds of things. So a, algebraic. Let's put an example there just to be specific. So for example, x squared. T, that's got to be trigonometry. So T for trigonometric. That is again confusing because that's trigonometric in nature, it just happens to be an inverse trig function. But by trigonometric, we mean sine, cosine, the other four trig functions is primarily what's meant there. And finally, E stands for exponential, such as, say, e to the x or maybe phi to the x. Yeah, go ahead.
So I saw it online also, Elante.
Oh,
Is that also, the first one can be first or no?
E,
For instance, IL8, it's just like where the I and the L are first. It's IL8.
it's probably just as good. Yeah, it's gonna depend because these are not perfect. The way I've always learned it is with the L going first. And so I think most of the problems that I see in my notes and in this book work with this acronym pretty well. If a book starts going this way, they might have a different set of problems where that's just the better approach for them. Unfortunately, there's no perfect approach at all. It's just a good starting point. So what I would suggest is if this isn't working out, change it up and maybe try going with a different direction, IL to start out first. And that might be a best approach for that kind of situation. Other questions or comments about that at the moment? Okay. So we've
So-
done a lot, but we haven't done one integral. Oh, sorry, go ahead.
So for this acronym, you wouldn't use it like PEMDAS where like one takes priority over another. Like it's just whatever you see in the equation.
It is kind of a priority kind of thing. So say, for example, let's take a look at, how about, yeah, this one right here. This one looks like it'd be exciting. So if we were doing this problem right away, then I would see there's an algebraic, this portion, there's a logarithmic, and I would think of this as a precedence going top down. My U would be LNT for this one, since this one in through this mnemonic takes precedence. Does that make sense with that idea there?
Yeah, that makes perfect sense. Thank you.
Yep, you bet. It seemed to be suggesting an exponential function, say, for example, e to the x or 7 to the x is your last pick. But again, this is not a perfect mnemonic. It's just a way to get started. And sometimes, just like U substitution, you just want to try something until something sticks and you've got a right antiderivative. That's exactly what we'll do in example 3, but other questions first? Okay, so here's where the course really starts in earnest. These are what the typical homework problems are going to look like. First, we have x, hyperbolic sine x we want to deal with. And for going through this guidance right here, let's maybe take this along with us as we go, just for a easy reference. What would you all say is a good choice for you to get started in integration by parts? I agree with you. And notice that this mnemonic isn't even perfect. Hyperbolic sine doesn't even seem to fit anywhere here. It seems like it would fit mostly with trigonometric, although it's a hyperbolic trigonometric function in that sense. But if I see something that looks algebraic, like an x, that's often, but not always, a good choice for you. Let's just set u equals x. And really with integration by parts, this is step 1. Let's write this out carefully. In the homework, there's a little bit of a guide on what is expected for the work. Let's take a look. We're being asked, if you're using a U substitution, indicate what U is. But if you're using integration by parts, we need to build out this table. It doesn't have to be in a table form, but we need to indicate U, dV, du, and dV. I might have said that twice. I'm going to make a correction there on that. Let's go back here. Step 1 is to set U. I would say step 2, you might do it in a different order, but once I have U, I immediately want to get dV. Kind of a strange table. You start with a U, and then next you're starting with a differential for the next stage. Anyone see what dV must be at this portion? Exactly. Our goal here is to take really everything inside here. If U is X, the remainder, everything else is going to be dV. So let's put that in as sine hx dx. So that's our step 2. Step 3, we need a differential. So in this column, if your u is x, du is going to be the derivative of x is 1, which multiplies dx. I would just write that in as a dx like that. If you put in a 1 times dx, that is absolutely factually correct as well. But dx is considered a variable, so it can simplify algebraically to just dx. Now we go to step 4. And this is interesting. When we went this way, you're differentiating and combining it together to make a differential. When you're going this direction, you're taking an antiderivative. It's always the most simplest antiderivative. And you would write this out as v equals cosh x. The derivative of hyperbolic cosine comes out as positive hyperbolic sine, and that's our antiderivative. Yeah, that's a great question. I've heard it cosh, but that was from Dr. Palmer. You would have to ask him to know for sure. I've heard cosh maybe for one guy, Dr. Palmer. So yeah, Dr. Palmer is into all sorts of things like differential geometry and such. So I think cosh is probably pretty standard. I would have to ask him at this point though, to be sure. You can either say hyperbolic cosine, but that takes a lot of oxygen, but cosh would be probably very well understood. Yeah, go ahead on Zoom.
I've also heard cosh, and then I've heard it pronounced cinch for sine h.
I've heard that one as well. Yeah, cinch and cosh are the two I say a lot. But when it comes to like secants, I usually just say hyperbolic secants, just to be specific. Well, we did it, folks. That's the start of the table. I do want to add just a little bit of notes to this. I think sometimes getting your V is the most confusing thing about building out the table. So if it seems kind of funny, here's a reminder. To get V is always going to be the antiderivative of sine h x dx, which came from whatever you put here. So you're literally just finding an antiderivative, but you're putting in the most simplest antiderivative, so no constant. Yeah, go ahead. Gotcha. Yeah, that's one thing that's really weird here. Sometimes we require that constant. Here, we put in, let me see where I can put in some notes. We want the most, or take the simplest antiderivative to get that. So we wouldn't add a constant c in this kind of situation. Move that out of here now that we had got the table. So once we decide on this, there's steps 1, 2, 3, 4. Step 5 is just to finish out the whole rest of the process. So let's call this step 5 right here. Exactly. And building the equation is a great way to say it. When you're looking at this technique for the first time, there's a lot of value in literally just writing out uv minus the integral of v du. So that came from either our derivation right here, or probably this is a good place to look. It's better looking. It's nice formatting there. So copy in that equation, because once you have that, it's the structure. You just go and look up your parts and plug them in. So here's how it goes. First, you multiply u and v together. So I would write in, for u, it's an x. For v, it's cosh x. Then at this stage, I'm just going to copy in the rest of the structure minus the integral. And then more substitutions. It says v du. When it's referring to v du, it's just saying multiply those two together, put it in the integral. So the v is cosh x, and the du happened to be just a dx in this problem. So at this stage, we're not done, right? We integrated a little bit. I have part of the answer, and now this original, quite complicated integral has been cornered into this position right here. Once we solve that last integral, we'll put in the overall constant of integration, and the process will be over. So let's give this a try. First copying esh cosh x minus antiderivative of cosh x. Any volunteers for what that should come out as?
Sine h.
Exactly, we get the sine hx on that one. And I like these derivatives because they never flip signs on you on this thing when it comes to cosh and sinh, sine h and cosine h. Last thing we have to put in is the constant of integration C, and we're home free. That's the essence of integration by parts. We did it, folks. How does it feel getting through that one? Does it make sense? Awesome. It's has a lot to do with this right here. Getting through this table is what enables you to write down the formula, which, let's be honest, is a weird looking formula. But now when you know what all the parts are meant to be, you get the integral cornered into something that's more solvable. You are on the right track if this, something complicated, resolves down to this, something more simple. If I came down here and this was harder or as hard as the original integral, I would want to start over right there. So that's the essential approach to this kind of technique. Essentially what we have going on in the first few sections of this course is pretty much this experience. Problems and solutions, reviewing integration, differentiation techniques. So let's keep on going and see how to deal with this one next. Any questions at all first, folks, with the full run through on part A? Okay, we've got about 27 minutes. Looks like we might finish this one off when we come back on Thursday's class, but no worries. It's probably reasonable to go a little bit slower in the first week of class. So what do we have going on? We have w squared, that's an algebraic function. E to the power of negative 2w, that's an exponential. So that suggests a good start on this one might be let me maintain the color coding. Okay, I'll do blue for Hugh. I would say a good choice for you ought to be the w squared on this one. That would be an algebraic function. So let's go w squared. I personally, after I get my u, I go for the dv. dv equals, it should be everything remaining. So e negative 2w dw. And now we have to do two more things. So I'm going to copy a problem down as a screenshot just for extra motivation on how to go through this. So pause that thought right there and let's steal this one. Okay, back to our problem. Hide that a little bit more. Once you have row 1 down in this table, notice it's a little bit weird. It's a u and a differential, so strange to start out. But the next thing is you just do a du. Anyone see what this one should come out as for this differential? We get a 2w and a little bit more.
dw.
Exactly. So if the variable starts off as u, you get your du, the derivative here, 2w, and then just slap it with a dw. So that one's completed. Now over here, you know it's not too bad, but you're finding an antiderivative right here, and it's no different than an antiderivative of this. It's just not going to be written with the integral sign necessarily. So here, I would absolutely avoid the u substitution. If you do a u substitution within the integration by parts table, your problems start to get really, really long, and that's a good thing to avoid if you can. I would integrate this in the same style we integrated this one. Completely sideline the u substitution. We already know the antiderivative of an exponential is itself. We just need a corrective factor right here so that when we check the derivative, it'll come out right. Well, over here, note we had a 3. We said antiderivative is negative cosine, but then we put a third in so that when we differentiate and the chain rule comes into effect, an extra factor of 3 wipes out the 1/3. Same idea here. If it's linear, the power of w is a degree of 1. All you need to put in is a negative 1/2, and you did it. You completely skipped integration by parts. That's the simplest antiderivative right there. That's something that becomes really common in a class like this one, even more common in Calculus 3, I'd say. You don't always want to do every single u substitution, but that's weird getting used to after Calculus 1, I'd say. How do folks feel about it? Does it make sense on how we did this one here? Okay. Well, if we're happy about it, here's what the next step is going to look like. I almost always do this I mean, even in my own work, when I'm reviewing this before a class, I almost always go like this. UV minus integral of VDU. And it's only because there is a lot of information we're trying to convey here. It's good to have the structure laid out and then just plug in the information. So left to right, use W squared. And the W squared is combined with V, which is -1/2 e to the power of -2W. I'll have to put parentheses in there to recall that there's a -1/2. -1/2 e -2W multiplying. Then we go minus and put a little bit of space before the integral sign. When it says VDU, you're taking all of this, multiplying all of this. So, well, there's a bunch of constants and stuff that you have to worry about. You do save a lot of time if you just multiply those constants right here. That's not great on the notes then. It might not be easy to see what I even did. I typically, on the notes, will take this 2, put out in front. And this -1/2 multiplies it, so there it is, a -2. I'll resolve all the constants like this so that we just focus on the good stuff, the function itself without the constant. So everything highlighted in yellow still multiplies in. And now we have a W, e -2W, dW. This might be a good place to pause and a bit of concern as well, because we mentioned this is working if you go from an integral that has reduced complexity. Did we really reduce the complexity over here? It's kind of debatable. But you know what we did do is we dropped the power of W by 1. And that can only happen so many times. So this is actually progress. But this is one side effect of doing integration by parts with higher powers. I need a whole nother integration by parts right here, so we have to do it a second time. In fact, if this was to a power 7, you'd have to do it 7 times, and now there's a whole tabular shortcut for making that happen effectively by hand. I'm not going to assign or ask those questions on exams. Highest powers you'll see is power 2. You'll use integration by parts at most twice in one single problem, rather than 3 or 4 or 5 times. That could take pages. So we'll put down a line here and redo integration by parts on this integral. That means we should be really careful. I would put a bracket around this integral. This is going to turn into a +1, but if this settled to, say, negative or -3, whatever constant's here distributes into the result. So not big danger on this one, but other problems we'll see. Good idea to put a parenthesis before you go to the rest of it. So next thing we're going to do is integration by parts. Again, this acronym is still in effect. And if we reduce the complexity once to get to a slightly simpler integral, we just reuse the same exact strategy. Let's let UBW. We'll let dV be equal to everything else. And notice you don't have to think as hard on this one, really. I'd still be careful on this differential. Du is the derivative of W, which is a 1, and then it multiplies dW. So it's often just written in this format. But for everything else, this is a direct copy. If dV is still e -2W, then V itself is, once again, -1/2 e -2W. It's kind of nice. You don't have to reinvent the wheel if you're going through this a second time. On the next step, we have -1/2 W squared e -2W. Over here, this is +1, so we're just lucky. We didn't need those parentheses this time, or the brackets, so I'll drop them at this stage and go plus UV minus the integral of V du, where this is the new table that we're going to work out on this portion here. Any questions at the moment, folks, to that stage? Kind of tedious to have to use integration by parts twice. These are not the most common problems, but this problem is here and here on the homework as well, just because it's good to know that's something that can happen. So let's keep on going. -1/2 W squared e -2W plus, now we go carefully. U is a W, and it's gonna multiply this right here. So there's the U, V is going to be -1/2. E -2W. Then we have, oh, this portion next, so minus the integral. I'll put in the minus sign, then again, a little bit of space before the integral sign. Pick out your function v, it's gonna multiply du. So let's first take that -1/2 and pull it out. E -2W goes inside. And then a dw. So we've got it, folks. This is the last part. Once we solve this integral here, we're home free. Yeah, go ahead.
Did you get the 2/2?
Let me take a look. Oh, these right here, I just canceled as a +1 altogether.
Oh, okay.
So I canceled the negative signs and this just became a 1. So I dropped it on this next step.
Hmm.
So it really should have looked like this. This would have been a better paper trail, a 1 times going right there. Other questions so far? Okay, so let's take a look. Here, this is just a constant that's going to become a +1/2. And we're pretty much just writing down our end answer here. Lots of copying on these longer problems. -1/2 W squared e -2W. I'll go over here, put the constant out in front, it just looks better, less parentheses, -1/2 W e -2W. And by the way, if it looks better, it's easier to tell if it's correct. So sometimes trying to clean things up is definitely a mathematical pursuit. This turns into a +1/2. But what would you get for this portion right here? Anyone see what that should come out as? Exactly. Really, it's just this same thing right here. So the moment you found V once, you're in fact doing just literally this. So just to convey that, this portion right here is just going to come out like this again. So here's another -1/2 e -2W. The method's done, so at this stage, we throw in the constant c. There is kind of an unfortunate amount of writing in some of these problems. And for me, I would have probably put a -1/4 to avoid having to put in another line. The reason I write all this in is it's just hard to see what even happened in the notes unless I put that in. So keep in mind, you don't have to put in as many steps as I do on your notes and your work. If you see something that you know that's a -1/4, put it in at that line. Otherwise, it's a little bit extra copying, but let's get it in. The answer is -1/2 W squared e -2W minus 1/2 W power 1 e -2W minus 1/4 e -2W plus a constant c. That's a lot of writing, but that's integration by parts in a nutshell. Oh yeah, we could factor out a 1/2 e -2W. We could do a lot of really cool things to this one. And that's one thing that's, excuse me, kind of tricky with the calculus class is even knowing where to stop. I would say this is a very acceptable answer. We're trying to simplify these kinds of things, combine like terms, cancel bases and such. But if you format your answer like say this, factor out a -1/2. Let's see, we also can take out e -2W. Then this is just a nice stylistic way to format your answer. Never required, but sometimes the back of the book does do these kind of things. And so sometimes it can be of value. So let me write the total answer this way. We're going to have a W squared here. We'll have W power 1 here. Let's see, we factored out -1/2, so this will be +1/2. Constant c goes here, and that's another way to format your answer. But just to emphasize, both are great answers. Well, any questions, folks, with either way of formatting the answers or getting through that whole process? Let me see if I can zoom out on this. Okay, so sometimes these problems get really long. This is one of those long versions. And the homework exercises are kind of strange. When you go through the problems in the homework set, I think a lot of people, me included, have an anticipation of, 3's quick, 5's quick, but a little bit longer. That's not the case. Some of these are fast, some of them are long. It's actually kind of mixed. It's really kind of strange how these exercises get put together. Well, let's try out another one. Any questions whatsoever, folks, on part B here? Okay, moving ahead in our adventure, carry in our mnemonic. And the book does something similar to this one. I don't think they do a cosine inverse. They have one where it's just a natural logarithm. This kind of thing is tricky, I'd say. And what's surprising to me is that it is honest integration by parts, even though it doesn't look like there's even enough parts to make that happen. Usually you think integration by parts, something like this. Something is being multiplied inside an integral. But not in this case. This is just cosine inverse x. So our hands are kind of tight here. There's no option for u really. I'm just going to make it cosine inverse of x. If we do that though, I don't see what dv must be in this case. What's left for dv? Exactly, it's just dx now. So if u is cosine x, cosine inverse x rather, dv is just the dx. Kind of strange looking. Here's the tough part. Again, if you don't have this derivative memorized, that's okay. I think it's easy to forget how some of these go. And for full disclosure, when I wrote out these notes on, I think Monday, I did review this so that I recalled. There are tricks though. If you're differentiating a co-function, you should expect a negative sign. So I would put a negative there. And it turns out sine and cosine inverse both involve the same denominator. So it would go like this for the derivative. But that's a weird one. Again, that's part of the handout for exam 1, these kinds of derivatives for inverse trig functions. I'm not expecting you to have perfect recall on every single element of calculus 1. Well, if u is cosine x, that's its differential. Here we have a differential, excuse me. So the question is now, what was v on this one? How about someone on Zoom? Anyone on Zoom see what v should be here?
X.
Exactly, good call. So it seems weird, but yeah, if you take the differential of this, you get dv equals dx. In fact, we've done that, it just looks funny because we start often with, say, u is w, the differential is dw. So what feels unnatural about this table is we're just doing it backwards now. We're integrating and picking the simplest antiderivative. Now that we're here, we're just about there. Let's write this in as equals uv minus the integral v du. And now we're just throwing in each of these components. So u and v is just taking these two. I'll write that in as x cosine inverse x minus the integral sign, and then a little bit of space because we have some constants to consider. For the portion that goes v du, you're just taking this and this, multiplying those two together. But same conflict with the constant, it's just convenient to take that negative one, put it over here. Now we don't have to worry about that. It'll just be an x. It's multiplying a fraction with a positive one, so down below will be root 1 minus x squared. And a dx. So that's how it all comes together. We just have one more integral to solve. And again, here's the test. This is working out if you went from an integral that's hard to an integral that has reduced complexity. That just depends on who you ask. That looks more complicated. There's more stuff. But you know what? That's easier to solve. Anyone know the method to solve this remaining integral? Oh, that's a good question. I think the trig sub could work on that one. I think a u sub might be a better choice, only because we haven't gone into trig substitution. But good eye, that might be a good one to try on a trig sub for this one. We'll come back to trig substitutions when we're in section 7.3, so those kinds of things are coming up. Let's go for an ordinary u sub. We go for a u substitution. You're looking for a function that's going inside another function. Anyone spot what that ought to be? Absolutely. So that one is going inside the square rooting function, making that one a good call. Now, once we have the u, we take its differential. Du is going to be equal to a negative 2x dx. The next step is a stylistic choice. I like to take and just solve for the x dx, divide out the constant. So I would personally write this out as negative 1/2 du equals x dx. And so now we can take this and this, x dx, and just swap it in for a negative 1/2 du. Looks like we're home free on that u substitution. So putting it all in, the next step is a lot of copying. X cosine inverse x. From here, I have a positive sign, but I'm also going to throw in this negative 1/2. So it's going to go negative 1/2, integrate. X dx are gone. They're becoming du with that negative 1/2 put in. And now it's 1 over square root u altogether. So once we solve this, the whole problem is complete. This is a good stage where if you find that it's just going to be too much copying line by line to solve something simple like this, you might split the problem up at this stage. Let's do that right here to illustrate. Sometimes it's not a bad idea to just separate out something you're solving, like that integral. 1 over root u du, and we'll solve that one on the margin and just plug it back inside right here. So strategies for solving this one are, you want to re-express the radical sign as exponent. This is a good calculus 1 kind of review material right here. This is 1 over u to the power of 1/2 du. And some people solve this one right at that step. I'm always astounded that people can do that. I personally am not a person who's good at that. Every time I integrate that kind of thing, I always go like this, or I'm going to get mixed up on my directionalities. I take the base u, promote it to the numerator. Its exponent has to swap to a negative. And to me, this is way, way easier to integrate than that one would have been. The way we integrate this, it's just a power function. We put a little bit of space in front. U, step 1, power goes, excuse me, power goes up by 1. So just add 2 over 2 to that negative 1/2. And you'll get a positive 1/2. Next, you divide by the exponent, which if it's a fraction, just multiply by the reciprocal, which is 2. Add a constant, and you're just about there. Other than, just don't forget, u is actually 1 minus x squared. So if we keep on going, we could say it's 2. Power 1/2 right here, we can write in as a square root. The u you see right here can be re-expressed as 1 minus x squared plus a constant. And now at this stage, we've solved this integral here. So this is now that. We have to put it all together for full credit, so we never want to celebrate early on this kind of problem. If you did leave your work just like this, if this is a 5-point problem on homework, you might lose 1 point with a small comment. Don't forget to show this full answer. So here's the last formality. The total answer is x cosine inverse of x. Let's see, we have a constant of negative 1/2 right here. That's going to multiply this constant of 2. And when that happens, we'll just get a negative sign. But let's show those step-by-step stages right here to see how it all really comes together. I'm going to put in a negative 1/2. And I'm going to do something that looks like I am violating an algebraic rule. So let me know if you catch it. Plus c. So what I do, I went kind of against some of my advice originally. When you solve this one, this negative 1/2 had to distribute through this entire answer right here. So why is there not a negative 1/2 times c? Anyone see why this is allowed?
Because you already included the u.
Sorry, say again?
You already included the u to the negative.
That's part of the answer, but not the total answer. There's a small, weird, subtle thing going on with that constant c. Yeah, go ahead. It absolutely does. The reason for that is, yeah, it's any real number whatsoever. It could be 0 squared of 270 million plus pi, anything at all. And an arbitrary number like this multiplied by a constant is still an arbitrary number. And so traditionally in this kind of context, we don't even worry about -1/2 multiplying through. If you put in -1/2 times c, that's an arbitrary integer just as this one is in its own right. So there's no difference either way. So here, it looks a little bit funky, but that's a special c representing any real number. So we're allowed to write it out in this more simplified kind of way. So our answer is finally x cosine inverse of x minus the square root of 1 minus x squared plus a constant c. Well, we did it, folks. That's part C altogether. We still have about 3 more problems on these notes that we want to take a look at. We're going to finish off a stranger looking one. You might have noticed that definite integrals have been neglected, so let's see how integration by parts interacts with those. These shouldn't take too long when we come back on Thursday, so we'll probably also start off these notes right here by thinking this due date will be pushed a little bit forward. The due dates become official the moment we finish off this section. So this one will be due officially on the 29th of August, when we are 1 week away from when we finish it next class. Well, any last questions or comments, folks, before we call it a day here? Okay, at this stage, I'd say you can get through most of the homework. Some of those problems we haven't directly addressed, so you might get stuck here or there. So if you want to wait a little while before you start, I think that's a fine strategy. Folks who would like to start homework earlier, I think you could get through the majority of the assignment. So if you like working in that route, that's pretty workable as well at this point. But have a great night, folks. I'll see you all on Thursday's class. Hopefully my voice doesn't give out. I get used to talking for lengths of time, usually by week 2 or 3, I think.
Thank you.
You betcha. Have a great night, folks.
Thanks.
Any questions?
Do you know how to use this access code and stuff?
Well, this access code right here, let's see, is for the WebAssign portion.
Yeah.
But on our course, we're not using WebAssign at all. So,
Oh, okay.
or let's see here. You might also use it to get your access to your textbook. So,
Yeah.
Are you-
I got the paper textbook.
oh, you got the paper? Oh, yeah. So this is just if someone was using a WebAssign along with their course. If you've used WebAssign before, I should mention, I could set it up so that you could get in there and work those kind of problems, but
Yeah, I've never used it before.
gotcha. Yeah, I'd say not worry about it then.
I was just making sure.
Gotcha.
So, make sure.
Yeah.
7.1 is 3 through 31, page 490. When I click on the PDF, it's blank page, it shows 4, so these are the questions.
Yeah, it's not really 3 through 30 yet, through 31, just those particular selected questions.
Right.
Yeah. So you could either grab your original textbook, or if you want to use the PDF, it's just the same exact problems.
Sure.
Unless I made a typo.
I was
Yeah.
trying to see a PDF scan.
Oh, gotcha, yeah. I've done that before, but I started to realize that the publishers usually think of that as some kind of behavior where they want to send you a cease and desist letter, so
Sure.
I'm just trying to type them up instead. I hope whoever comes after me doesn't come after me. I don't think so. Yeah. That's funny you say that. I've seen websites where people have sample problems for studying, where they literally took this stuff. It looks like from a textbook, and they just put in here x cubed, different problem now. So I've seen some weird study reviews like that.